Okay, so we're going to continue on a problem started in the previous video in which a block is sent up an inclined plane of inclination theta with initial speed v0. The block goes up, there's friction, the coefficient of friction between the block and the plane is mu. The block goes up here, then turns around, it comes back. And we want to know the time it takes to come back to the original position where it started. Now, this problem is tricky for a variety of reasons. Going up, coming down. First of all, it's not one that has the same acceleration in both parts. It doesn't come back with the same initial speed that it has. Energy is lost. You'd find out in one of the later chapters when we cover energy that this is got some non-conservative forces on it. But we're just using Newton's law to work this problem. And we had to first solve it for going up the inclined plane because we were able to show during that part of the path that it had a constant acceleration using Newton's law. And then we also found the time and the distance that it went up the inclined plane. Now that we have the distance, we can start it from 0 and have it slide back down the inclined plane back to where it started, so that this distance is whatever the x we had in the first part of the problem, and the final x will be 0. And the initial speed is now going to be 0, and the final speed we don't know. So we've got a new thing. We got a block here, x naught. We know Vx naught is 0 meters per second. When it gets back down to here, x will equal 0 meters based on our previous coordinate system. And let me put the value of x in. The value of x was v naught squared over 2g. To remember it. And then it had the mu cosine theta plus sine theta, I think. I'll check that just to make sure. Okay. No, I'm sorry. V naught squared over 2g mu cosine theta sine theta. So that's right. So we got another kinematic equation problem, except we got a new acceleration. So I'm going to write down all these things down here in the table. X naught v naught squared 2g mu cos theta plus sine theta, x 0 meters, Vx naught 0 meters per second, Vx don't know, time down, I'm going to use small d, don't know, and acceleration I know right there. I was asked to find the time, so I want to find t. Well, x is x naught plus Vx naught t plus 1/2 times acceleration ax sub d t squared. And I'll put little d's to indicate that's the time down. I can simplify that equation a lot. This is 0. This is 0. So I can solve this for TD because I know x naught and I know everything else here. So let me put that in, if you would. So 1/2 axd times td squared is minus x naught, and we have already got what x naught is right above it. So this is minus v naught squared over 2g times mu cos theta plus sine theta. Or if you preferred, it was minus v naught squared over 2 times the acceleration up. And that means TD squared is going to be, I'm going to bring a 2 over here, so minus 2 2g. I had the v naught squared up here, and then I'm going to have this mu cos theta plus sine theta, and another g, and then I'm going to make sine theta minus mu cos theta so that I can pull the minus sign out so that I can cancel this minus. These two cancel, and that looks pretty ugly in the bottom, I will grant you, but not as ugly as maybe you think. This is V naught squared. This is G. This term here, this looks like A plus a B, and this looks like A minus B. And when you take A minus B times A plus B, you get A squared minus B squared. So doing that, I get sine squared theta minus mu squared cosine squared theta. So it doesn't really look as bad as you might think, like I said. Take the square root of both sides and take the positive root. TD is V naught over G square rooted sine squared theta minus mu squared cosine squared theta. So that is the time it takes to come down. Now to find the total time, we have to add the time down to the time up. So T is TU plus TD. Well, both of them have this term V naught over G. The first one has the term sine theta plus mu cosine theta. And the second one, the downtime, has 1 over the square root sine squared theta plus mu squared cosine squared theta. And that is, in fact, our final answer to the problem. But as always, we're going to want to ask and see if this makes some sense, and see if there's any unusual, funny things that happen. So, by the way, I missed. This should be a minus. My fault. That's a minus. What if mu squared cosine squared theta was equal to sine squared theta? What would happen if that term went to 0? Well, what would happen is this term's okay, but if this term here happens to be such that it's equal to that term, we get the square root of 0 in the bottom. And that means that this time goes to infinity. Now, why is that? The reason that that's the case is this. While the block is guaranteed to slide on the way up, it's not guaranteed to slide on the way back. If the friction is sufficiently high, the block will go up and stick. Let's see if we can see that. If I solve that, I find that mu would be the sine of theta over the cosine of theta, which is the tangent of theta. This is the condition for static friction. So, in essence, if this thing was to reach that point, this thing would be at the point where it would stick, where the friction force is sufficient that it could not slide down. And the reason for that is, on the way down, the friction force is opposing gravity. Let's go back and look at that in our free body diagram. The friction force here on the way down is opposing gravity. So if the friction force is great enough, it can make it so that it's not possible to accelerate down the incline. On the way up, you might notice that they're helping each other. So they're adding. And so you don't have that issue. So it's guaranteed to go up. Something else that's interesting. If you drop this to 0, you have to be a little careful, because when you drop this to 0, then the only acceleration then, you have no acceleration due to the weight. The only acceleration you have then is due to this part from the friction, and it will never reach to the point where it will turn around. So when we did the downside here, we have implicitly assumed that it comes down. And because we did that, we would not expect our formula to make sense at theta equals 0. And in fact, it doesn't make sense. Okay? Because it should never come back to its original place. So there is no, this formula here is not valid. Not valid unless it comes back. Which means that this sine squared theta has to be greater or equal to mu squared cosine squared theta, or this equation is not valid in any way, shape, or form. Okay, that finishes this particular video.